Hi everyone. Today we're going to go through the different states of matter. So this I think is lesson 1.3 here. So again, make notes for yourself here. So basically, we're going to start off really basic back to grade 9, maybe even earlier than that when you first talked about matter. So matter is defined as anything that has mass and takes up space. As part of the grade 7 science curriculum, you might have been exposed to the particle theory of matter. So this is a theory that states that all matter is made up of particles. So it is clearly a circular definition here there. So the particle theory of matter, all matter is made up of tiny little particles. So it's the arrangement of these particles that determines the state. So we've got our different states. The states are solid, liquid, gas, and those are the three that we normally talk about, and we're also just going to add in plasma as well. Now, matter can change states with, there's two changes. So in science, when we write a change, we use a triangle, right? So that would be the Greek letter delta, and it represents a change in. And you probably would have seen that in your grade 10 science course with the physics unit there, the motion unit. So matter can change between states with a change of, so if you were in class, I'd ask you to think of it, and most of you would come up with a change in temperature, right? So if we change the temperature, we can usually change states. Well, we can always change states if you get the temperature hot enough or cold enough. But there's also a change in pressure that can also change states, and that's because of the pressure pushing against the particles and changing them that way. So when we change states, these are physical changes. In grade 9 you would have talked about physical and chemical changes here. Just always remember here that chemical changes, when you have a chemical change, something new is produced. So that's sort of the key for understanding the difference between physical and chemical change. Chemical change, you have a new substance being produced. Physical change, often it's just changing states. Okay, so we're going to go through the different states of matter. We're going to start with solids here. So solids, first of all, if we were to draw our solids, solid particles are going to be right next to each other, okay? So we would draw them sitting together very, very close. Solids have fixed volume and shape. Now, the particles vibrate. It's one thing people often don't know. So the table that you're sitting at or the bed you're sitting on, for example, technically those things are vibrating. Now, we can't feel it because it's so small, but they're not completely static. They're slightly vibrating, and the particles tend to stay in position. Now, if you were in class, I'd get you to clasp your hands together. So I'm just going to get you to look here. So right now, clasp your hands together and then slightly move your hands like they're vibrating. So those are solid particles. So they're vibrating very slightly. When heated, particles in a solid are going to expand slightly. Now, if they're arranged in a sequence, it's called a crystal. So this is a diagram of salt here. So we've got the sodium is the blue balls here, and the chlorine are the green ones. And so we can see here with NaCl, I'm just going to change pens here. So this is NaCl. So for sodium chloride, this is table salt. They're arranged in a very distinct, organized way. So always in a 1-to-1 ratio. And this particular, the sequence is called a crystal when they're arranged like this. Now for salt in particular, we call this a crystal lattice. So this type of crystal is specifically called a crystal lattice. And I have a joke for you. Why did the chemist put salt on his salad? How else was he going to get the lattice in? Ha ha ha. Always got to have some lame chemistry jokes here. Now, If the particles are arranged randomly, it's called amorphous. So make sure you can understand the difference between crystal and amorphous. So crystals, obviously, like when you look at a grain of table salt, it's a crystal, it's very beautiful. Amorphous things, they're not going to have that kind of clarity. Light's not going to be able to be reflected from it. An example here is PB, and so of course, what does PB stand for? And some of you right now are thinking lead, but if it was lead, it would be like this. So it's not lead, and PB is, yeah, you got it, peanut butter. Peanut butter is defined as a solid, and it would be amorphous, okay? So it's an example of something being amorphous. Now, liquids. Liquids have fixed volume but no fixed shape, and we know that they're going to take the shape of the container that they're in. So if we were to draw our picture of our liquid particles, they're going to be a little further apart than the solids, but they're actually still quite close together. So still draw them fairly close together, but those particles are going to take the shape of the container that they're in. Now, they do have a fixed volume, which means, you know, if we have 1 liter of a liquid, you can't make that bigger or smaller. It's always going to be 1 liter. You can change the shape of it, but the volume will stay constant. Now, the atoms move in a liquid, but they do stay relatively close together. So I couldn't find a good picture for this, but if we look at this guy here, so take your hands and clasp them in front of your body, and then kind of move your arms. So wiggle your elbows, move your arms, kind of like you're doing the wave with your hands. Those would be liquid particles, so higher energy, but they have far more movement than the solids did. Thirdly, we have gases. So gases here have no fixed volume or shape, and the particles are free to move independently. So if we're going to draw a diagram here, I'm going to draw a flask that has a stopper in it. So it's sealed. So the gas particles are going to spread out throughout the whole container, okay? They're going to fill the space. So no fixed volume or shape. They're going to again take the shape of the container they're in, but there is not a constant volume. They're going to expand or be compressed based on what they're in. And particles are free to move independently. So, oh, my link's not working. If now, in order to show, use your hands to represent it. Here's the person. This is you. And take your hands, take your arms up. And these are hands. And shake them around. This is jazz hands. Okay, so gases. These particles are free to move. They have lots of energy, lots of movement, okay? Those are our gases. Now, plasma. We're going to talk about plasma today, but realistically, we really won't talk about it anymore. As chemists, we're more concerned with the solid liquid gases. So plasma acts very similarly to a gas. It is, and this is always an interesting word, people say this word differently. Some people say gaseous, some people say gaseous, some people say gaseous. So however you want to say that word, it's a mixture that is in a gas state of electrons and cations. So of course, electrons we know are in atoms, right? Those are our electrons. Cations are positively charged ions. So positively charged ions. So it's a mixture of those. So they're actually the most common form of matter in the universe. Examples, northern lights are made up of plasma. Tried to see some this summer, did not see any this summer. Hopefully you guys did. Lightning, stars, those are all made up of plasma. Plasma exists at high temperature and low pressure, and they are used in thermal plasma reactors, and they respond to magnetic fields. Now, the reason why they respond to magnetic fields, of course, is because they're charged particles. We've got the electrons and the positively charged ions being the cations. Now, we're going to go through different properties. So there's 4 properties we're going to talk about, and then we're going to talk about how put them in a chart and say how they relate to the 4 different states of matter. So our first one is compressibility. So if something is able to be compressed, so I want you to try to think of a definition for compressibility, or you would take your hands and see if you can like make a motion that you, if you were playing charades, that you would communicate to someone what compressibility is. Okay, now quite a few of you will probably be doing something with your hands where you're pushing them together, right? So compressibility, the definition, we can define that as being able to occupy less space. So if something has the property of compressibility, they can occupy less space. Next, we're going to talk about is density. So what is density? So I want you to think of these 2 things here. So we have 2% milk versus cream. So most people have had experience at some time in their life with looking at the difference between the 2% milk and the cream. Now, most people, like, we know that the cream is a lot thicker, right? Then it pours slower than the milk. But if I asked you, which one is more dense, what would you say? So I want you to just take a second and come up with an answer. Now, most people would say that the cream has a higher density. It's false though. It's a bit of a, this is one of those things where when we just think about things, we don't come to the right conclusion. Density is defined as mass per unit volume. Now, table cream is actually lighter than the milk, and if you had a container, you would see milk being here, and then you'd get the layer of cream sitting on the top, and then that's where the fat rises. That's where if you're on a dairy farm, they'd scoop off that top and you'd be able to make butter out of that. So sometimes what we think is not always accurate, right? So density doesn't actually have anything to do with a thickness. Density is just mass per unit volume. So if you've got the same volume of something, which one's going to be heavier, okay? So that's how you define that. Diffusion. So diffusion is movement of molecules from one area to another, and most people see this in their biology classes because we talk about things diffusing across a cell membrane, for example. And an example of this would be something going from high concentration to low concentration. So these particles would come through the membrane here, or they would diffuse. So diffusion, movement of molecules from one area into another. Flow. So flow is another one. Yeah, this one's interesting. When we think about flow, again, most people would have a really hard time thinking of words to define that. And if I asked you to use your hand, you'd probably make some sort of a river flowing motion with your hand. But putting it into words is really difficult. But one way to define it is the property of being able to pour. So if you can pour something, it has the property of flow. Now we're going to go through here and put our different states. We've got solid, liquid, gas, and plasma, and we're going to talk about the 4 different properties. So number 1, solid. Can you compress a solid? Can you make a solid take up less space? Sometimes people think yes here, but they're really just changing the shape of it. Like if you cut something up, for example. If you cut something up, you're not actually changing the volume, you're just changing the shape. Or some people will think of a sponge as an example. But a sponge has a lot of air pockets in there, right? So that would be different. So can you compress a solid? No. Can you compress a liquid? Also no. So putting pressure on them is not going to make them take up less space. Can you compress a gas? This one, definitely. And we see that in our regular lives all the time. Any kind of aerosol can would be a compressed gas. Can we compress plasma? Again, the answer is going to be yes, because plasma is going to act the same as gas for all of these things. Now, density. Now, remember that density is mass per unit volume. So which of these, so solid, liquid, or gas, which one is going to be the most dense? Which one is going to have the most mass per volume? And hopefully you came to solids here. So this is going to be a high density for a solid. Liquid is still pretty high, but I'm going to put mid. Gas would have a very low density. Gas particles don't really like each other. They want to get away from each other. Now, diffusion. So do the particles or molecules move from one place to another? If you put, if you have an eraser and you put it on your desk, does that eraser go anywhere? No, it doesn't. So unless there's outside forces acting on it, no, it is not going to go anywhere. Liquid, will it diffuse? Yeah, liquid will diffuse. It will spread out a little bit to a point, right? Gas, will it diffuse? Yeah, so if you spray perfume on one side of a room and if you spray a perfume, eventually you're going to be able to smell that perfume on the other side of the room, right? So yes, it does diffuse, which means plasma also diffuses. Okay, next, the property of flow. So does something have flow? So solid, can you pour a solid? No, you cannot pour a solid. Can you pour a liquid? Yes, you can definitely pour a liquid. Now, this is the tricky one. Can you pour a gas? That's our big question mark. And I'm going to do a demo in class and we'll figure that out together. So you can wait for tomorrow's lesson for that. Okay, thanks. Now, exercise 5 is now assigned. So finish that up and we'll correct it in class next day. Thanks, guys.